Okay, chapter 4 is on volumes of revolution. We're going to, this is just extension of what you did last year. So let me remind you of how to find the volumes of revolution around the x-axis. So this is when it's rotated by 360 degrees or 2 pi around the x-axis. So let me just do a little diagram here, a drawing. So there's a function y equals f of x, and then if you are going to rotate that area under the curve around the x-axis, then you're going to do a full circle, so 2 pi. You're going to rotate it around there, you will get a shape, and you're going to find the volume of that shape. So it's like that all the way throughout by integration. So the volume is simply pi times the integral between the limits a and b. Now you're rotating, and then those y values, these are the radiuses of each individual circle that you would have got if you imagine slicing that shape, 3D shape, along each y value. Y would be the radius, so that's why it's y squared dx. Okay, if it's around the y-axis, then I know you could have something like that, maybe. It's being rotated, and then you could see it's rotated around the y-axis. There's the y-axis again through 2 pi, so you're getting this one is like a nice, maybe, I don't know, hemisphere. This time it's going to depend on the axis here that are being rotated. The axis will be your the radius, so the volume, and you could say the y here, so it's around the y-axis. This one could be vx, so it's going to be pi times let's say this is the limit again, a and b, so between limits a and b, x squared dy. This time you're going to integrate with respect to y. Okay, let's do the first example. We are going to find the finite region between 0 and pi over 2 that's rotated around the x-axis. So let's just show you what sine 2x looks like. So if I draw a sine curve, so normally it goes through pi here, but because it's 2x, so been shrunk, so it's pi over 2. And we're going to find what we get if we rotate this lamina, if you like, around the x-axis. So first of all, let's quote the formula. So it's pi modulus, the limits are clearly 0 and pi over 2, and it's going to be y squared dx. So it's pi 0 pi over 2 sine squared 2x dx. So the rest is just simply integrated. So remember sine 2x, sine squared 2x, the formula for this one, it can be derived by using, it needs to be changed to cos 2x. So 1 minus 2 sine squared 2x is cos 2x. So sine squared 2x is going to be cos 2x, 1 minus cos 2x over 2. So we're going to have pi, and we've got 1 minus cos 2x. You can put a half in front of it, or just put over 2. I'll put the half in front, there you go. So you're going to get 1, which will integrate to x, and minus cos 2x will go to minus a half sine 2x. The limits are 0 and pi over 2. Okay, so put pi over 2 minus a half sine 2 times pi over 2 minus, these both will give me 0 if I substitute 0. It's important to write this lower limit, evaluate it anyway. So it's going to give me pi over 4, because this is just going to give me 0 as well. So that's example 1. Okay, just to note, it should be pi squared over 4, because it's pi over 2 times pi over 2. Example 2, this time we're going to talk about, we'll go through an example on volumes of revolutions around the y-axis. So here is the function y equals 4 ln x minus 1, and we've been asked to find the volume, exact volume of the solid generated by this region R being rotated by 2 pi radians around the y-axis. In fact, we are asked to show that it is going to be the following expression. So let's first of all quote the formula. So Vy, because we are rotating around the y-axis, pi, the limits are going to be here 0 and 4. We're going to use x squared dy. Okay, so what is my x squared? So if y is equal to 4 ln x minus 1, then let's make ln x the subject. So it's going to be a quarter of y plus 1. So x is going to be e to the power of a quarter y plus 1. Okay, so if we square it, that will give me e to the power, if you multiply 2 by a quarter, you get a half. Perfect. So in our question, we are going to keep the limits of 0 and 4. Squaring this gives me a half. Y, I'll just separate these powers. Okay, so let's integrate it. It's a simple integration. This will go to itself, and then you need to divide by whatever the power differentiates to. So that will give me e to the power of a half y plus a half over a half, which is obviously the same as 2. So it's pi. So put the limit. So I've converted to dividing by half by into multiplying by 2. The first limit is 4, so it's e to the power of a quarter, so a half times 4 plus a half, minus 2e to the power of 0 plus a half. Okay, we're keeping it in exact form, so 2.5 is 5 over 2, which is 2.5, let me write it like this, minus 2, and this is 0.5. Okay, so it's just because then it will be obvious that I can bring the factorize e to the power of a half out, and you'll be left with 2e. Oh, and let's bring 2 out as well. Let's have 2 squared minus 1, which gives me 2 pi root e squared minus 1. So once you start subbing the limits in, gaze over to what you are aiming for. Clearly that made me think, rather than writing the powers 5 over 2, to keep it as decimal, but 5 over 2 would work perfectly as well. Okay, so have a go at exercise 4b, which is all about volumes around the y-axis. Okay, the next section is 4.3. Section 4.3 leads to exercise 4C, and it will be immediately after example 3. So this time we are talking about both around the x-axis and around the y-axis, but using parametric curves. So let me just remind you of what the formula is for finding the volumes of revolution around the x-axis. So this is what it looks like. So it's pi, and then you've got y squared dx between the limits a and b. Now, what happens if you have the curve, the same curve? Let me just draw that curve here. Maybe there. So a and b. This one is rotated around the x-axis. What happens if it's, rather than be defined in Cartesian with the Cartesian equation, it has been defined in terms of parametric equations? Then you need to integrate with respect to those the parameter that's being used. So if x is some kind of function of t and y is another function of t, then we are going to change the variable to t, and we're going to integrate everything with reference to t. So you'll be able to express y, it has been expressed in terms of t already, so you substitute, but then we've got to change that dx to dx, dt, and then dt. So if you notice, we've had y squared before and dx. So this is as if those t's, dt's cancel to give you, to show that it's exactly the same expression. Well, it won't be. Here, a and b represent the x values. So we need to change those values to t. So we need to find what t is when a is equal to, x is equal to a, and t is when x is equal to b. So that's the only thing, is you copy as it is and then just stick this over dx, over dt, and then dt at the end. Let's do something similar for the volumes of revolution around the y-axis. So at the moment you recognize that, let's keep, this time my y values are a and b. So a and b, let's rotate that around the y-axis. So x squared dy. Okay, so we are just going to apply the same method as before. That's going to stay as pi. These limits would need to be changed to t's. X squared can be expressed in terms of t, but then at the end you should have your dy, and you will add that extra bit of dx. dt. There you go. So effectively what you need to do when you've got these two definitions, you will have to, for the volumes of revolution around the x-axis, you take y squared and times it by the x differentiated. If it's the volumes of revolution around the y-axis, you will take the x squared and then square the x's and then times it by y differentiated, and then integrate the result. So let's have a go at doing this example. This region R between the limits 0 and 2, notice these are x values, it's going to be rotated around the x-axis through 2 pi radians. So the formula around the x-axis is going to be pi. Here we're going to use our t's when x is equal to 0, t when x is equal to 2, so those are limits here, and you're going to do y squared and then dx dt dt. Okay, so we'll have to find what y squared times dx dt is. Let's just do it here and then sub it back in there and integrate. So dx dt, okay, let me just find what dx dt is. So if x is equal to t plus t squared, then dx dt is going to be 1 plus 2t. And y squared is going to be 1 over 1 plus t squared. So altogether I have 1 plus 2t over 1 plus t squared. Let's change the limits. So when x is equal to 0, I need to solve it. So t times 1 plus t is 0. That gives me t is 0 or t is minus 1. Not sure which one yet it's going to be. So let's find what y we get if we put, yeah, so clearly y is greater or equal to 0. So that won't be any good. So also, when you put y equals 0, you'll get 1. So that would work. Okay, actually 0 works. So, but minus 1 will not work, because if you put t equals minus 1, clearly it's outside the region. So it's t equals 0. Plus it won't work for this value. So at that moment, this t is going to be equal to 0. And then when x is equal to 2, t plus t squared is equal to 2. So t squared plus t minus 2 is 0. So that nicely factorizes. Plus 2 minus 1. So t is equal to 1 or minus 2. But we're going to pick 1 because minus 2 is outside. So here we'll have t is equal to 1, and here t is equal to 0. So these are our limits. So we've got 0 over here, we have 1 over here, and then y squared times dx dt is simply 1 plus 2t over 1 plus t whole squared dt. Okay, so let's have a go at integrating this function. So you've got 1 plus 2t over 1 plus t squared. If you want to make it a little bit easier for yourself, replace that denominator with u. It just makes it a little bit easier. So du dt is 1, so du is dt. Just show, you'll see straight away. So you've got t is equal to u minus 1 here as well. So you've got 1 plus, substitute u minus 1, and then you've got u squared du. Okay, so you've got 1 over u squared, so u to the power minus 2, 2u over u squared, so 2u to the power minus 1, and minus 2 u to the power minus 2 du. So actually these two are the same, there's minus 1 of them. So add 1 to the power, divide by that power, so you've got minus u to the power minus 1 over minus 1, and then add 1, this one is going to go to ln, add 1 to the power, divide by power, it doesn't work. So you've got 1 over u plus 2 ln u. Change the limits. So my t was equal to 0 here. So when we change it was to use, if t is equal to 0, u is equal to 1. When t is equal to 1, u is equal to 2. So it's 1 over 1 to 2, and then 1 to 2, the limits. So the answer is 1/2 plus 2 ln 2 minus 1 plus 2 ln 1, which is 0. So it's going to be 2 ln 2 minus 1/2. Okay, but don't forget, I think this is actually a very common mistake. Once you write pi once, you forget to write it again. We've had a pi in front of this integral, so it's going to be multiplied by pi. Okay, so you can go on to exercise 4C, which is on parametric integration.